So the first talk of today will be given by Zijing on coating liquid films down vertical fibers. Zijing got his master's degree from Chinese Academy of Science and PhD from Nanyang Technological University in 2016. He was then a postdoc researcher at Cambridge, and since 2020, he's a professor at Harbin Institute of Technology. And so, yeah, I can hand over to Zijing if you want to share your opinion.
So thanks for inviting me to give this talk. And I would like to thank Professor Paul Linden for inviting me to contribute a research to celebrate the GKB 100th anniversary. So I'm going to talk about coating liquid films on a vertical fiber, the full Navier-Stokes problem. Actually, this is not the first time I talk about this problem at Cambridge. I talked about this topic, a similar topic, about 2 years ago in Cambridge, but something new has been discovered. Okay, firstly, I would like to introduce the experimental background of this problem. And about 20 years ago, Kliakhandler, Davis, and Backhoff, they performed a series of experimental study of liquid films flowing down a vertical cylinder. And the thickness of the liquid film is relatively thicker than the cylinder radius. So this is a so-called thick film flow. And they changed the flow rates to investigate how the flow rates influence the flow patterns. So when the flow rate is high, they observe that the large droplets, which are moving at constant speed, are separated by a thin and long and flat thin film, which is defined as the flow region A. And when they reduce the flow rate, they observed a necklace-like flow structure, which is called a flow region B. And they reduce the flow rate further to a very small flow rate. And they observed that a large droplet can coexist with several tiny beads. And a large droplet will catch up with and consume the front small beads, while in the back region of the large droplet, new tiny beads will be born because of the Plateau-Rayleigh mechanism. And Kliakhandler et al., they try to explain the 3 different flow regions by using a thick film model. I will not talk about that thick film model because in their study, it seems that the thick film model can't predict the wave dynamics in the 3 regions. Later, Crest and Mata in 2006, they proposed a symptotic model, which is called CM 2006 in this talk. And they tried to compute the first traveling wave solution of the asymptotic model, and they compared their traveling wave solution with the experimental data. For example, in the flow region A, although they predict the wave speed, their predicted wave speed seems to be in excellent agreement with the experimental data. We find that the wavelength in the experimental study is not the same as what is used in the Crest and Mata 2006. Later, Ryukyo et al., they tried to model the inertial effect and the streamwise diffusion effect, and they also consider the same wavelength as Crest and Mata 2006. They can improve the wave speed, and they think the fluid inertia plays a very important role in this system. However, we find that the second problem is the two models fail to predict the flow region, the dynamics in flow region B, because we find that the flow region B is not a long wave regime. A last model, which is very similar to the Rilke et al.'s study, is energy integral model proposed by Navier and Oren 2009, and they neglected the streamwise diffusion effect. And we find that they correctly use the wavelengths from the experiment, but their predicted wave speed will be higher than the other models. So we think that there might be something wrong in the studies, and we should find out which one is a key reason that causes the poor prediction of the flow region A. And also we want to address the prediction of the wave dynamics in flow region B by dropping the assumption of long waves in that models. Another problem, actually I call this the third problem, is that the predicted wave speed in flow region C is not consistent. In 2006, Crest and Mata, they predicted the wave speed is about 30% to 40% higher than the experimental value, while Rilke et al., they used the Crest and Mata's model and recomputed the wave speed. And they obtained a very close wave speed to the experimental data. And we also computed the Crest and Mata's model, but we obtained the same wave speed as Crest and Mata. Another observation is that the energy model proposed by Navier and Oren actually is identical to Rilke et al.'s model as the first order approximation, but we can find that their predicted wave speed are very different. So we think there might be something wrong in the computation of the weighted residual model, but I'm not going to compare my results with the study by Rilke et al. The last problem we find that is in the previous studies, they try to compare the traveling wave solution, which is steady, with the experimental data in flow region C, which is unsteady. Although I and Ashley suggest that the flow region C should be compared with relative periodical orbit, but our prediction of the wave speed is poor. So the question is that why do these models fail to predict the wave dynamics accurately, actually for all the three regions? So there are two reasons which might be clear. One is the long wave assumption. The second is the inertial effect. The other might be something else which will be explored. So to answer these questions, our starting point is the full Navier-Stokes equation. So we try to solve the original problem by dropping the long wave assumption and include the inertial effect. So we just follow Crest and Mata and introduce two different length scales. One is the radial length scale, which is chosen to be the mean film radius computed from the flow rate by assuming a laminar velocity profile. And this flow rate is measured of a saturated state. So the other length scale is the length scale, which is the length scale in the axial direction, which is the capillary length. And the velocity scale is chosen by balancing the gravity and the viscous force. The pressure scale is given by rho GL, And after choosing that scales, we can non-dimensionalize the governing equations. We get two dimensions parameters. One is a Laplace number, and the other is the Bond number. The Bond number is typically small, which is about 0.3 in experiment. And if the Laplace number is small, we can assume that the inertial effect is not important because the Bond number is very small. Then we use a domain mapping technique to map this wave interface, this domain with a wave interface into a regular domain. And we impose theoretical boundary conditions in the flow direction. And then we try to use a Fourier Chebyshev spectrum method to solve the problem. And we also validate our code by comparing our solution of the Navier-Stokes equations with long wave solution. And this has been this code has been validated by considering a rotating cylinder, which has been published in GFM in 2020. And we just use our in-house code to investigate the classical problem. Actually, the cylinder is not rotating. And the first step is to just follow the previous studies and check how do the streamwise diffusion effect and the inertial effect influence the result. So we set the initial mean radius of the film is to be 1. This means the initial mean radius is identical to the mean radius calculated using the experiment data of flow rate. But unluckily, we found that the predicted wave speed, for example, for the flow regime A and the flow regime C, is even worse than the model equation proposed by Prescribe and Mata. And we are confused about our results for several days. And initially, I just thought maybe there's something wrong in my code. So I tried to check my code for several days, but without discovering the bug. And then we tried to monitor the evolution of the flow rate, and find that the flow rate is not conserved. So the initial flow rate is connected to the final final flow rate of a saturated state by a heterokinetic orbit. And this is very crucial because all the previous work thought that the flow rate is conserved, and the flow rate of the final state was used to compute the initial mean radius. And this is the major reason that causes the poor predictions of the wave dynamics in the 3 regions. And then we try to find the true initial mean radius that will correspond to the final flow rate. And by doing a bisectional method, we can find that the true initial mean radius. And here I just show 2 plots of the relationship between the initial mean radius and the flow rates. For example, if we choose the initial mean radius to be 1, the final flow rate, the dimensionless flow rate will be around 0.2, which is higher than the experimental one, the dash line. The dash line indicates the experimental flow rate in flow region A. So this is the direct evidence that we can't set as far or the mean initial radius to be 1, but we should adjust the value to be about 0.97. And then we apply this procedure to flow region B and flow region C to get the correct initial radius. And finally, we recomputed the traveling wave solutions of flow region A and flow region B. But flow region C, we failed to get a converged relative periodical orbit. It might be caused by the very small time step in my code. And we try to get a solution of flow region B using direct numerical simulations by designing initial condition. And we find that by matching the flow rate in the numerical study and the flow rate in the experimental study, we can predict the wave dynamics correctly in all the flow regions, especially in flow region C. The previous study reported that the predicted wave speed is about 30 to 40% higher than the experimental value. And in our study, this has been improved to 3%. So by discovering the bug in the modeling work, we fixed the gap between the theoretical predictions and the experiment. And we finally get the current best results. Yeah, I think it's time. So the major conclusion from this study is that to predict the correct dynamics in liquid film flows, the flow rates of the final states rather than the initial states in the numerical studies should match the experiments. And we also conjecture that more accurate predictions by the models can be achieved by matching the flow rates with the experiments. Okay, I would like to thank my collaborators on this problem, Dr. Ronald from Queen University of Electronics and Technology, and Dr. Ashley Willis from Sheffield University. Thank you very much. I would like to take questions now.
Well, the first question is, what kind of code do you use?
Oh, I wrote the code in MATLAB. This just directly inverse the matrix. You know, it's a bit confused to explain the code. It's not like the channel flow because of the wave interface, and all these variables are coupled together. So when I try to solve the equations, you need to solve a big matrix for the velocity and the pressure, and then you just invert the matrix to get the variables. If you need the code, you can email me. I can share my code with you.
Okay, thank you. Second question from Tim Pedley. Do you do any experiments show non-axisymmetric behavior?
Well, there was a recent study about this problem. Actually, an experimental study published in Physical Review Fluids, and they tried to use some non-symmetrical initial conditions and get non-symmetrical patterns. I think, well, this can happen when the surface tension is large and the initial perturbation is large. But from the viewpoint of linear stability, the asymmetrical mode is always the most unstable. So in my study, I didn't find any non-symmetrical pattern if I perturb the interface by small disturbance.
There's another question. Is it possible to prescribe partial wetting, non-wetting conditions in the code?
Well, it's easy to impose a slippery boundary conditions, like Navier slippery boundary conditions in the code. It's not difficult.